We have talked about elastic properties of bodies. We talked about the law that governs the concept of elasticity. So in this our class now, we need to see how we can use some of these questions and solve problems. We use the formulas, we use the laws, the formulas that we have generated from Hooke's law, Youngwood laws, and solves these sample questions that we have on the board. So let's look at the question. Question 1 says, a spring of natural length, a spring of natural length 3 meters is extended by 0.01 meter by a force of 6 Newton. What will be its length when the applied force is 15 Newton? This is a very simple question. The first thing you need to do is to bring out the information given to you. Bring them out, extract them. The natural length of the material, a spring of natural length is for 3 meters. That's the natural length, the original length before the application of force. 3 meters. It's extended. The extension is 0.01 when by a force of 6 Newton. So when they apply this force of 6 Newton, this material that is 3 meters long, it increased in length by 0.01 meter. So the extension now, if we come here and say solution, the extension is 0.01 meter by a force of 6 Newton. The force is 6 Newton. So if we put it based on Hooke's law, because Hooke's law is a very fundamental law that explains this process. It talks about extension and load. So if you put it, Hooke's law tells us that F is equal to what? KE. Our F is given, which is 6 Newton. Our E is given as what? 0.01. Our E is given as 0.01. So what is the value? How do we get the K now? This one becomes 0.01 K. Here is 6 Newton. So we say K now, our K becomes 6 divided by 0.01. K becomes 6 divided by 0.01. So at the end, it gives us the elastic constant, or the force constant is what? 600 Newton per meter. That is the value. 600 divided by 0.01 is 600 Newton per meter. But this is just the force constant. The question said, what will be its length when the applied force is 15 Newton? So you go back to your equation and say F is equal to KE, where the relationship, where K now is what? 600. We say F is equal to 600 multiplied by E. What will be its length when the applied force is 15 Newton? The length, the extension, this material will increase in length. When what? It will increase to a certain length when a force of 15 Newton is applied. So let's put it and say 15 is equal to 600 times what? E. 15 is equal to what? 15 is equal to 600 times what? E. Such that our E now is 15 divided by 600. 15 divided by 600 will give you 0.025. If you divide this now, you can say 5 here. 5 here will give us, okay, say 0.025 meters. That is the value that it will give us, 0.025 meters. So this is the extension of the material when a force of 15 Newton is applied. But the question says, what will be its length? What will be its length? Remember, the original length is 3 meters. So the new length of the material now would be the natural length plus the extension. So the length of the material, length of what? The material is equal to the natural length or the original length plus what? The extension. So the natural length is 3 plus 0.025. So it gives us 3.025 meters. This is the length of the material. Length of the material when 15 Newton is what? Applied. Is the length of the material when the force of 15 Newton is applied to the string. That was the solution to our question 1. Question 2 in our sample question. Question 2 talks about a force of 500 Newton. Question 2. A force of 500 Newton is applied to the steel wire cross-sectional area. The area is 0.2 square meter. One's original length is 0.1 meter. The extension is given as 0.01 meter. We are asked to calculate the stress. So our stress, say F all over what? A, force per unit area. The force is 500 divided by the area is 0.2. So 500 divided by 0.2, it gives us what? 2,500 Newton per square meter. That's what we have. That is for the stress. Let's look at for the strain. The strain says extension over original length. The extension is given to us in the question as 0.01. 0.01. The extension, yes, 0.01. The load, the original length is what? 0.1. So we have the extension, which is 0.01 divided by 0.1. So our strain is equal to what? 0.1. 0.1. Remember, I told you that strain is a dimensionless quantity. It's a dimensionless quantity because it's a ratio of to what? The same units. Then let's look at the third one, Young modulus. Young modulus. And we have that one E, we say stress over strain. Stress is we have calculated stress as 2,500 divided by the strain, which is 0.1. So our 2,500 divided by 0.1 will give us the Young modulus becomes what? E. When you say 2,500 divided by what? 0.1. 0.1. So 2,500 gives us what? 25. Can give us 25,000. 25,000 Newton per square meter. That is the value for that. So let's quickly look at question 3 before we go. Our question 3 talks about a spring is stretched 40 millimeters by a force of 15 Newton. What is the work done? The work done, let's quickly look at it. The work done, when you talk about the work done in an elastic material, the work done in an elastic material is the same thing as the energy stored in an elastic material, and you can also call it the elastic potential energy. The work done, or we call it energy stored in elastic material is the same thing as the elastic potential energy. Elastic potential energy. How do we calculate this? The work done here is 1 all over 2, the 4 times what? The distance. 1 all over 2, the 4 times the distance. And this expression is the same thing as if you say 1 all over 2, then you recall that our F is equals to KE. Are we together? If F is equals to KE, that means this our expression here for work done. We can substitute F into this equation. Your work done, you can also use 1 all over 2. Where you have K, you change it to KE, and you have our D. And you know that our D is the same thing as our E because it's also the same the extension. So you have 1 all over 2 KE what square. 1 all over 2. So that is a simple derivation or explanation of the work done, or you call it the energy stored in elastic material, or you call it the elastic potential energy. So let's use this formula now and see how we can solve this sample question 3. A spring is stretch 40 millimeter. 40 millimeter there is the extension. So you have the E here is giving us what? Is giving us 40 millimeter. And remember, we said 100 centimeter we have what? 40 millimeter. 100 centimeter will make what? 1 meter. 100 centimeter will make 1 meter. So that means 1000 centimeter will give us what? 1 what? Meter. So in this case, we need to convert this millimeter to meters. So we have 40 divided by 1000. So it gives us 0.04 meters. It gives us 0.04 meters. And the force is given. Force is given in the question as 15 Newton. The force is given as 15 Newton. They say, what is the work done? So the work done now, our work done is equals to 1 all over 2. The force is given F force E, which is 1 over 2. F is what? 15. Extension is 0.04. 1 all over 2. So if you have here 2 here can cancel. 2 here is 0.02 can cancel. So we have 15 multiplied by 0.02. 15 multiplied by 0.02. So if you multiply 15 by 0.02, you have what? 0.3 joules. 0.3 joules. Because the work done, the SI unit of work done is what? Is joules. So that is the value for this. So please like this video, subscribe to this channel, and share it with your loved ones. Have a wonderful day, and God bless us.